Hello and welcome to the next video for 9.6 inverses. This video is going to be, we're just pretty much going to dive into this one. We've found inverses last time, right? So just a reminder on how to find an inverse given a function and then how to graph it. So I've got this function here. Find the inverse of the one-to-one function. So it's already told us it's one-to-one. Don't worry. This one's one-to-one. We did the math for you. F of x is equal to 2 minus 3x over 4, and then graph both on the same coordinate system. Sounds good. Well, how do I find this inverse? I think I'm actually going to start by graphing this guy because I think we need a reminder on these types of linears. Yes, they are in fact linear. They have a degree 1. There's no squared, no square root, no anything like that. But this doesn't look like our classic linear. So just a reminder, you can split this up. Sorry. And rearrange it so that you get negative 3/4 x plus 1/2, and you get a classic y equals mx plus b form. Okay, so that was a quick reminder on that. If you need more help, by all means, contact your teacher and get a refresher on graphing linears. So up 1/2 and down 1, 2, 3 over 1, 2, 3, 4 gives us a very poorly drawn this line here. Okay, ignore that. Now I'll just make it better. It's fine. There we go. Okay, that's much better. So this is our original function. For those of us not working in colors, we can label it f of x. All right, either form is fine for finding the inverse. I'm going to go with the original format because why not? Maybe we were supposed to do that first anyway. Remember, to find an inverse, ditch the name real fast. You don't have to ditch the name. I just personally think it's awkward to put f of x into a function when we have just a singleton letter that we can use and there's no difference to it. Technically, you could leave it as f of x. I think that's weird though. Go ahead and switch x and y. We actually have to do that inverse step, and then we're going to solve for y. So we multiply 4 to both sides, subtract the 2, and divide by -3. And we get something that looks pretty similar to the first one, this being our inverse. Again, that's not super easy to graph though, so let's go ahead and split that up. We get 4/3 x, oops, I'm sorry, -3. So we get -4/3 x plus 2/3 is our f inverse function. Okay, so then we go over here, we go up 2/3, which is a little higher than last time, and then we go down 1, 2, 3, 4 over 1, 2, 3, something like that, give or take. Okay, you might be thinking, how on earth are these inverses? That looks totally horrible. There's no way these are inverses. If we graph the line y equals x, which runs kind of like that, we can see they're kind of equal. They're symmetric over this line. Yep, so symmetric over the line y equals x. Again, I'm graphing on an iPad, so of course it's not going to be perfect, but this, you can see at least it's a general reflection over the line, which looks good. All right. Let's do it again. Find the inverse of this function being a rational, and use it to determine the range of your function. Verify your answers analytically. Okay, analytically can be done in a couple ways, so we'll come there in a minute, but let's start with just finding the inverse of this function. Actually, you know what? Before we do that, let's state the domain of this function. Because they want us to find the range, you may as well find the domain, right? So the domain of this function, remember with rationals, there is something that will quote unquote break these, something that will not allow us to get an answer, and that's having 0 in the denominator. So in this case, numerator doesn't matter. We can plug in anything we want to the numerator, but I don't think we're going to have 1 in the domain. So -∞ to 1 and 1, to infinity would be the domain of this function. Just a quick reminder on that, right? In interval notation, we would say x does not equal 1, right? That would be our set notation, or our interval inequality notation, pardon me. This is our interval notation. All right, now that we have that, let's go ahead and see if we can find the inverse. Go ahead and switch x and y. This one is going to be a little complicated because I have 2 occurrences of y, which is a problem if I'm trying to solve for that y, right? So I think the bigger issue right now at this moment is still the fact that y is in the denominator. So I'm going to move that to the other side. Since I have y's on both sides, I want to eventually combine them. I am going to go ahead and distribute my x, get rid of some parentheses. Then I'm going to move that y-ish looking thing to the other side. 2y plus yx. Now oops, pardon me, that's really ugly y. I'm going to factor out a y, 2 plus x. So I've taken that y out, and then I can divide by the thing that is not x. All right, now hopefully that wasn't brand new, right? It's definitely still not easy, but it's something we have seen before this year. So there is our inverse function, x over 2 plus x equals g inverse. Oops. Cool. Now to use it to determine the range for the original domain. Why on earth would this be able to help us find the range for the original domain? Well, when you think about it, what did we just do? We switched the x's and the y's. The domain talks about your x's. So if we switch those, all of a sudden our x's are in our inverse are talking about the range of our original function. Domain is x's, range is y's. But if we turn those around, then our inverse has the x's talking about range and the y's talking about the domain of the purple function. So if we look at the domain of this new one, that's going to be the range of the old one. So what's the domain of this new one? It looks like everything but -2. We looked at, and then that is now the range of this guy. So we can go back in purple and say, oh, if we invert this, we can find the range pretty fast. In fact, we didn't even talk about how to find the range of rational functions because doing it with the original function is actually incredibly complicated. But if you invert it, it's super fast. All you have to do is find the domain, which we are incredibly used to. So we have found the range of the function. We're going to go ahead and skip the analytical part just for the video's sake. We'll probably do it in class. One more thing down here. What happens if you do want to invert a function that wasn't invertible, right? What could you do? There is a way you can actually fix that boo-boo. So we can kind of band-aid the situation a little bit. We can use what we call a restricted domain. So for example, we have our classic not invertible function here, x squared. X squared, great example of not one-to-one, great for the horizontal line test, fails almost every point. So what can you do? What you can do is add a, hey guys, only look at one side of this function kind of statement to it. You restrict the domain to one side. Once you do that, you've eliminated half of the answers that give you the same y's. So basically, you cut off the part you don't want. And there are reasons you might cut off the negative side. There are reasons you might cut off the positive side. It depends on the situation you're using it for. It's really up to whoever's creating the problem, whatever the situation is, but you can restrict your domain and then you don't have a problem. If I drag a horizontal line on this one, there's no issue. There's no double point, right? And so it is a quick fix boo-boo. Let's use that now to graph the same f of x, the same g of x function as before. We've already tried to look at this one back in the last video. G of x, x squared minus 2x plus 4, right? We already determined this is not invertible. But now it has been restricted to just, pardon me, the back side of the function. So it's just the left half, everything less than 1. If you recall, our vertex was at 3, 1. And so this is, I'm sorry, 1, 3. 1, 3. And so this is everything to the left of that vertex. Let's go ahead and take a look at it. Okay, we had the point 0, 4, 2, 4, and 3, 1. Instead of drawing this whole function, I'm only going to draw all the x's that are less than 1. And so that would be this side of the function. So I'm not going to use this point here. Now I have no problem inverting this thing. So let's go ahead and get a visual, visual representation of what this is going to look like. I have 2 points. I can invert those 2 points, right? Super easy. If I have 1, 3, I'm going to have 3, 1. If I have 0, 4, I'm going to have 4, 0. So it looks like my function's going to be an upside down, a negative square rooty thing, which makes sense because square undoing the square root, right? That makes sense. The fact that we chose the back half is going to give us a negative. Okay. If we had chosen the top half, we would have had a positive function, but we don't. We have this negative one here. So how do we solve for the specific function now? Well, this one's a little bit complicated because we do have 2 x's here. So if I have y equals x squared minus 2x plus 4, solving by routine, right? How do you find an inverse? Change the x's and the y's. 2y plus 4. The only problem is now I need to factor the y, and I can't. This doesn't factor. Nothing multiplies to 4 but adds to negative 2. You've got 1 and 4 adds to 3, some kind of combination of 3, and 2 and 2, which cancel each other out. And so this doesn't factor. And plus, we know it doesn't hit the x-axis, so we know it doesn't factor. So I'm going to have to use the quadratic formula. But it doesn't equal 0 yet. So first, I have to remove the x. And then I'm going to look at this 4 minus x as the c term. So if you recall, quadratic, we've got a, b, and c. We're going to do y is equal to minus b, 2, plus negative 2, plus or minus the square root of negative 2 squared minus 4. A was 1. C is now this binomial term. So we're just extending the idea a little bit to 1 over a to a. Okay. Simplify this. We get 2 plus or minus the square root of 4 minus, let's see, that would be positive, that would be 16. And that would be a positive 4x over 2. Clean it up just a little bit more. 2 plus or minus the square root of 4x minus 12 over 2 is actually a function. It is a function. Now remember, we've restricted this domain. Why do we have a plus or minus in our function? One's going to give the positive half of this function. One's going to give the negative half of this function. Which one did we restrict to? That's right, the negative half of this domain. And so this will be, our final answer. This is our inverse function. So g inverse here, or I'm sorry, in this problem it's j. J inverse is going to be 2 minus the square root 4x minus 12 over 2. You could simplify that if you tried really hard, but there's really no purpose to. All right. The last one for this section, and really the last one for this chapter, I just chose the same color, that was all, is a cubed root. A cubed root doesn't have any restriction. So this one's not going to be nearly as hard. Let's just start by graphing it. This is a cubed root function that has been moved left 2 and down 1. So remember, cubed root has these 3, and it kind of looks like this guy from one of our previous videos. Actually, I don't think we've ever talked about this. So cubed root is just a cube on its side. Okay, it's a cube on its side. But now these points have been moved left 1, 2, and down 1. So we're looking at kind of this guy. Okay, so here's our k of x. Just another parent for your toolkit, another parent for your toolbox. Cubed root. This one we can invert pretty quickly. We've got y equals the cubed root of x plus 2 on the outside minus 1. Switch the x and y. Whoops. Oh, don't do that. Don't change pluses to minuses and minuses to plus. And then we'll solve for y. So I'll start by adding 1 to the other side. Cubing because it is a cube root. And then subtracting 2. And so that will equal our k inverse. This one also doesn't have any domain restrictions, which is fabulous. So let's go ahead and graph that cubic that has been moved left 1 and down 2. So the cubic has also the same beginning points. And then left 1 and down 2. So we're looking at this guy. And we can see once again, yes, they are inverted over the y and y equals x. All right, that's it for section 9.6 and for chapter 9. This was a lot of information, some of which we've seen before. If you have any questions, reach out to your teacher.